Okay, in the last lecture we have been discussing about the three body problem, and for that once the z is equal to 0. So, we considered we were trying to find out x and y. So, in that course, so we have the body here which we wrote as m 1, another body was m 2, and we defined the barycenter somewhere here in this point as b, and then in the x y plane once z is equal to 0. So, in the x y plane we are trying to solve for the x and y. So, this was the point x and y in the synodic reference frame. So, in the synodic reference frame this is the x direction of the synodic reference frame, and this is the y direction of the synodic reference frame. So, for x and y, then we wrote for x, we solved for x and we wrote as 1 by 2 times mu 2 minus mu 1 divided by mu 2 plus mu 1 times r 1 2, where r 1 2 is nothing but the distance between the mass m 1 and m 2. So, this is r 1 2, and we were working out for y. So, the expression for the y that we got. So, we wrote y square as r 1 2 a square minus r 1 2 by 2 times mu 2 minus mu 1 by mu 2 plus mu 1. Okay, and we have already worked out for the r b 1. So, r b 1 this can be written as r 1 2 times mu 2 divided by mu 2 plus mu 1. Okay. So, substituting this into this place. So, y square then becomes this we have already done in the previous lecture. Okay. So, r 1 2 whole square minus r 1 2 divided by 2 times this becomes mu 1 by mu 1 plus mu 2 times r 1 2. Okay, so, r 1 2 can be taken out of the bracket throughout. So, this gets reduced to 1 minus mu 2 minus mu 1 divided by 2 times mu 2 plus mu 1. This whole square. Okay. So, this can be further simplified as okay. Therefore, y square you can write as r 1 2 whole square times 1 minus mu 2 plus mu 1 divided by 2 times mu 2 plus mu 1 whole square. So, y square becomes 3 by 4 times r 1 2 whole square. This implies y equal to plus minus under root 3 r 1 2. This is what I stated last time, that we are going to find out this value of y. So, ultimately we have got x equal to 1 by 2 mu 2 minus mu 1 by mu 2 plus mu 1 and y equal to plus minus root 3 by 2 r 1 2, and we have already proved that r 1 s equal to r 2 s equal to r 1 2, that is in this figure. This was the distance r 1 s and this was the distance r 2 s, and this is the distance r 1 s. So, these distances are equal, means the point x y along with mass m 1 and m 2, this makes a equilateral triangle. Okay. Moreover, we can see from this place, if we are assuming that, because we have already assumed that mu 1 is greater than mu 2, that is the mass of mass m 1, this is greater than m 2. So, if we multiply both side by g, so this will be written as this implies mu 1 is greater than mu 2. Okay. So, this we have already discussed all these things. So, mu 1 is greater than mu 2. So, this implies that x is, from this equation we can directly see that x is less than 0, that is x is negative. So, if we look on into this figure, so we are measuring the distances from this point, okay, and fixing a synodic reference frame here in this place, where the O is the origin of the synodic reference frame and B is the barycenter in this place. Okay. So, x is coming out to be negative, means the, if this is a smaller mass and this is a bigger mass. So, x is going to lie on the in this place, because on this side we have the negative x and x s, and this side this is positive, on this side this is positive and here this is negative. And y is both positive and negative according to the solution that we have got, plus minus root by 3 1 by 2 if r 1 2. So, from directly we can see from a figure here. Okay. This is r 1 2 and this is also equal to r 1 2 and this is also r 1 2. Okay. So, this forms a equilateral triangle, and obviously, then this distance which is y, okay, another point that we are getting downside. So, this point is minus on this side. In our case, we have taken on this side, this is the positive side of the y and this is the negative side of the y. Okay. So, both the points, they will appear as, this is m 1 and m 2, okay. This is point 1 and this is point 2, and barycenter is lying somewhere here. Okay. So, because it is equilateral triangle, so this is 60 degree and this will turn out to be root 3 by 2 r 1 2, and this will also turn out to be root 3 by 2 r 1 2 from the equilateral triangle properties. Thus, we have got a total solution of two solutions. So, one equilibrium point which is existing here, another equilibrium point which is existing here in this place. Okay. This is also called librational point. So, moreover from in this figure you can see that because these points are lying just on the same distance on both sides. So, we name this point as, if we name this as L 4. So, this will be naturally called L 5, and we have chosen x in this direction and y positive in this direction, and vice versa if we choose x positive in this direction, if we choose x positive in this direction. So, y will be positive in this direction. So, any one of them can be called L 4 and L 5. So, this notation is just arbitrary, and we initially stated that there are total 5 equilibrium points. So, the rest of the 3 they lie on this x. Okay. So, next we are going to find out where those 3 rest of the points are lying. So, earlier we have written the equation of motion in the synodic reference frame, and then we set there x double dot equal to 0 and x dot equal to 0. Similarly, we set y double dot equal to 0, y dot equal to 0, okay, and z double dot equal to 0 and z dot equal to 0 to find out the equilibrium points. Okay. And if you remember, so the equations okay, in our lecture number 17, these were the 3 equations that we were using, and here we set x double dot equal to 0, y double dot equal to 0 and y dot equal to 0, x dot equal to 0 and z dot double dot equal to 0. Okay. So, here the same thing is available to us. Okay. So, with this assumption, then we further worked and we now assume that, let us say z equal to 0, and moreover let y equal to 0. So, y z equal to 0. So, in this equation what we did, we put z double dot equal to 0. Okay. So, if we set equal to this, so the quantity which is present here, so we can separate out z from this place, and the quantity mu 1 by r 1 s and mu 2 by r 2 s, these quantities are non-zeros, and therefore, we put z equal to 0. That we, from there we found out that the motion takes place in this, the equilibrium point lies in x y plane. Okay. Once z equal to 0, so this implies that the equilibrium point lies in the x y plane. Now, if we look into the next equation, okay. So, this is the equation number 2 in the lecture number 17 that we have used. So, y double dot equal to 0 and x dot equal to 0. So, we are left with minus omega s square y, and on the right hand side we have this term. Okay. So, from here we can write minus omega s square y equal to minus mu 1 by r 1 s whole cube plus mu 2 by r 2 s omega square s phi, this is. Okay. Now, this equation will be satisfied for y equal to 0. Okay. This can be satisfied for, this equation gets satisfied for y is equal to 0. We have already worked for the when y was not equal to 0, and we solved the equation number 1 and 2 by putting x double dot y double dot y dot and x dot equal to 0. Then from there we got the librational points 4 and 5. Now, our effort is here to get the librational points L 1, L 2 and L 3. So, here we set y equal to 0, because this equation gets satisfied, and then we use this in the equation number 1 which is available here. Okay. So, if we set y equal to 0, then we have minus omega square s x Okay. So, this is our starting point here now. Now, R 1 is, this is nothing but R 1 s is equal to, we write this as in the simplified notation dropping the s. So, R 1 s square. So, this is x minus R b 1 square plus y square and plus z square. Okay. So, here y and z both are 0, this equal to 0, this is also equal to 0. So, this gets reduced to x minus R b 1 square, and this we write in this way. Similarly, R 2 s y square plus z square, this is 0, this equal to 0. So, this gets reduced to x plus R b 2 this magnitude square. Now, we utilize this two results in this equation. So, let us suppose we write this equation as here as equation number A. Therefore, we can write omega square is x is equal to, now omega s is nothing but the angular velocity of the two masses, two primary masses, and this is nothing but equal to mu by r 1 2 whole cube, and we have proved it many times. Okay. So, omega square is equal to this quantity, and therefore, we can write this is equal to this equal to minus mu 1 by r 1 cube 6 minus r b 1 minus mu 2 by r 2 cube times 6 plus r b 2. Okay. Now, utilizing the results, r b 2 equal to mu 1 by mu 2 r b 1, this we have already derived. So, again repeating here. So, from here we get r b 1 equal to and r b 2 from here we can get, and this will be mu 1 by mu 1 plus mu 2 times r 1 2. Okay. And if we divide mu 2 by, and mu 1 plus mu 2 is nothing but mu, this quantity is mu. Okay. So, we can write this as mu 2 by mu r 1 2, and this we write as mu 2 is mu star times r 1 2, and this we will write as mu 1 by mu times r 1 2. This will then become 1 minus mu star r 1 2. This is very easy to see. Okay, now with these results, this equation can be further simplified. So, this is the equation that we have written earlier. Okay. So, this can be further simplified and this can be written as minus can be cancelled out on both the sides. So, let us term this as the equation number, this is B. So, using equation B, then we get an S also we drop. So, omega S we simply write as omega, okay, which we have replaced by mu by r 1 2 whole cube. So, again we remove all the things and simply write mu by r 1 2 whole cube times x is equal to mu 1 by r 1 cube x minus r b 1 r b 2. Okay. Now, r b 1 and r b 2 just now we have found out in this place. So, we can insert into this equation. So, inserting r b 1 and r b 2 expression, we have mu by r 1 2 whole cube times x, this is equal to, now mu 1 is available. So, mu 1 we can divide this mu, we can bring this mu from here on the right hand side and we can write this as mu 1 by mu, okay. And r 1 cube is already we have written in terms of x minus this was r b 1, okay. So, x minus r b 1. So, r b 1 we have written as mu star times r 1 2. So, this is mu star times r 1 2 whole cube times x minus r b 1 and plus mu 2 by mu times x plus r b 2 divided by x plus 1 minus mu star times r 1 2 whole cube. So, now look into this. This we can replace as mu 1 by mu we have written as 1 minus mu star. So, this gets 1 minus mu star and r b 1 we can take common from this place. So, this will become x by r b 1 minus 1, okay, and r b 1 we can write outside. From here also, because r 1 2 is the magnitude of the distance between the point 1 and 2 and therefore, this can be taken outside of the modulus sign. So, this becomes r 1 2 whole cube x divided by r 1 2 minus mu star whole cube. Okay, here one more simplification in this place itself we can do. This r b 1 we have already written as mu star r 1 2. So, here we directly replace this in terms of r 1 2. Okay. So, instead of taking b 1 here out, we write here as r 1 2, okay, and here we will take outside r 1 2 and therefore, the quantity which will remain here, this is x times r b 1 was r 1 times mu star. So, this mu star will remain inside. So, this quantity mu 2 by mu is nothing but mu star. So, this becomes mu star and here also we can do the same thing, x, and r b 2 is 1 minus mu star times in r 1 2. So, we can replace this as 1 minus mu star this r 1 2 and outside r 1 2 divided by r 1 2 we can take out of the bracket here, okay, x plus 1 minus mu star, this is whole cube. See, this can be further simplified now. So, from here we have then okay. So, in this equation we can cancel out this r 1 2 r 1 2 cube r 1 2 cube. So, we can cancel it out on both the sides. Okay. After cancelling this, what remains r 1 2 r 1 2 here this in this place. So, this can be brought on the left hand side. So, we directly write here x by r 1 2 this is equal to 1 minus mu star times x by r 1 2 minus mu star divided by x by r 1 2 minus mu star whole cube plus mu star times plus 1 minus mu star this is here we are missing 1 by 2. So, we introduce here x by r 1 2. Okay. So, this is x divided by r 1 2 1 minus mu star whole cube. Now, putting x by r 1 2 is equal to capital X. Okay. So, the left hand side will become x equal to 1 minus mu star. Okay. Here one term we can cancel out. So, provided this quantity here, this is the quantity which is the modulus, we are writing the modulus cube. So, if x by r 1 2 is greater than mu star, we can cancel out one of the term and then we can write this as x by r 1 2 minus mu star whole square plus okay, and this we are going to replace this by capital X. So, we are replacing this by capital X. Take to the next page. So, in this equation this becomes left hand side is x 1 minus mu star divided by x minus mu star square plus okay. So, remember that mu star is a positive quantity and 1 minus mu this is also a positive quantity. Okay. And what we are assuming here that this quantity is greater than 0. So, see the implication of this. So, if we assume that x by r 1 2 minus mu star is greater than 0, okay, means x by r 1 2 is greater than mu star. Now, look into the figures, the normalized conditions that we have mentioned earlier. This is the mass m 1, this is the mass m 2 okay, and somewhere B was the barycenter. So, this distance we wrote as mu star and this mass we replaced in terms of 1 minus mu star, the right hand side mass we replaced in terms of mu star, and this distance we wrote as 1 minus mu star. Okay. So, the implication of this is x by r 1 2 minus mu star, this is greater than 0, means this mass is the tertiary mass or the the smallest tiny particle we are using, or the small mass which is lying here, which we have written as m 3. Okay. So, it is, and x direction we are taking here as positive and y is downward as positive. So, mass is lying somewhere here in this place. Okay. So, and therefore, the then x by r 1 2, which is the distance this r 1 2. So, on the normalized scale r 1 2 becomes nothing but equal to 1. Okay. So, after this normalization, this is the distance that we have written x by x is equal to capital X is equal to x by r 1 2. So, this is the normalized distance. So, now this is the distance from here to here, which is here appearing as capital X. So, this distance minus mu star, obviously this is a positive quantity from here. Okay. So, this is the one equation that we are getting here. Okay, after this simplification, so what we ultimately got, this was our main equation. So, this is our equation number, let us say this is equation number C, and this is our equation number D. So, in this C, equation number C, if we are using the point on the left hand side. So, this is the result that we are getting. Okay. If the point lies on the right hand side, on the right extreme, we get some other result. Okay. This will get modified. If it is lying in mid between, so we get some other result. Okay. So, this equation we can simplify further, and we can write this as x times this equation number D, equation D can be simplified further to give x times x minus mu star whole square times x plus 1 minus mu star whole square. This is equal to 1 minus mu star times x plus 1 minus mu star plus mu star times x minus mu star whole square, here also whole square. Okay, and this we termed as equation number E. Okay. So, this equation E is called a quintic. So, quintic is nothing but a polynomial of degree 5. Okay. So, this equation is of degree 5, and this will give you one positive root, and here obviously x in this case is positive. So, you will get only one positive solution out of this, okay, and that gives you the one librational point, which we will write as. So, this point we will write as L 3, okay. And on the right hand side. So, this is our point L 3, right hand side of this M 2 we will get another point which we will write as L 2, and in mid between we get another point which we will write as L 1. So, we still have to work for L 1 and L 2. Okay, now in this again going back to equation number C. Okay. If we replace in this equation x by minus x everywhere, so we get the new condition. Okay, that is the point once it is lying here over the right of the point M 2. Okay, this is the point M 2. So, if the point is lying right of this, okay, so the same thing can be written as, so x by r 1 2 we have written as capital X. So, this becomes minus x equal to 1 minus mu star minus x minus mu star divided by minus x minus mu star whole cube plus mu star times minus x plus 1 minus mu star. Okay. So, this equation is written for point, the equilibrium point right of M 2. Okay. So, now we can take out the minus sign here from this place, and this can be written as 1 minus mu star times x plus mu, and here also this becomes x plus mu star whole cube, and then here in this place this becomes 1 plus, okay, then mu star and minus sign if we take it out from this place. So, what we are doing, we are taking out minus sign from everywhere and cancelling with this sign. So, this gets us x minus one minus mu, and this also can be written as x minus 1 minus mu. So, this is the quantity which is okay. So, now we can see from this place, once we have written in this fashion. So, what we are assuming, again going back to this figure. So, we are assuming, we are already taking the sign of here, replacing this by minus x. So, we are assuming here that this distance is now positive. Okay. So, this will give us another equation. This is our 18. So, this gives us another equation which we can write as 1 minus mu star divided by x plus mu star whole square plus Okay, so this is our equation, next equation. So this equation we can write as 11, this is 12. So this was equation number E. So this we term this as equation number F. Okay, now from these two equations E and F, okay, this is our equation number F and this is equation number E. Now the same thing again I am going to explain in a rather very simple way. See exactly what we have done. This is our point M1 and this is the point M2. So, what exactly is happening? This is the barycenter here. So, about the barycenter, these two masses are moving with the angular velocity omega. Okay. Now, they will always remain in the same line, okay, because they have the same angular velocity. So, they will move about this barycenter. Now, if you look into the equation E, so equation we derived for the point which was lying here, which we wrote as L 3. Okay, on the left hand side. Another point we worked out which was lying here on the right hand side, which we wrote as L 2. Now, exactly what is happening here, look, this distance we have termed as mu star and this distance we have termed as 1 minus mu star and this mass as 1 minus mu star and this mass as mu star. Okay. Now, what happens in reality once it is a moving? So, this point is also moving, okay, because we are looking for the equilibrium points. So, equilibrium points means in the synodic reference frame this point will appear to be a stationary with respect to these two, means it will neither move in this place, neither move in this place, neither it will move in this place. So, if it is remaining here or either this point it is remaining here in this place only. Okay. So, you can see that what are the forces acting on this point in the barycentric reference frame. So, if you look from that point of view also, so it will give you very good insight. So, let us look it through the barycenter point of view. Okay. So, if we are taking the point number this the small mass m 3 here in this place or either a small mass m 3 here in this place. So, you can look that the force acting due to this bigger mass m 2 on this point mass m 3, this is on this side and also the force due to this will be on this side. Now, the whole thing is also moving like this. Okay. In reality what is happening, the mass m 1 and m 2 they are moving about their barycenter. So, the and if the mass m 3 has to keep in the same line. So, this also must move like this. So, what exactly we need to do here, that if omega is the angular velocity of this mass m 1 and m 2. So, omega square and times the normalized distance that we are showing, this is the distance x, okay, omega square times x, which is the something you can call this as the centrifugal force, or you can it is better to describe in terms of centripetal force, because the centrifugal force is not a good option. It is an because we are writing it from the barycenter point of view, and therefore, it is good to say here that this is a centripetal force. So, the to move this mass in the around this barycenter. So, the mass m 3 this will also be moving around the barycenter. So, to move this, the necessary centripetal acceleration this must be provided by the mass m 2 and the mass m 1. So, in this case both are acting in the same direction, the force due to the mass m 2 also acting in this direction and force due to mass m 1 is also acting in this direction. So, both of them combine. So, now we can write this. So, in terms of the normalized masses, so this is mu square mu stars, okay, and the mass of m 3 if we multiply on the left hand side and on the right hand side. So, that cancels out. So, you can yourself little bit explore it. So, this becomes mu star times the distance between this and this mass. So, this is the distance here, this distance we can write as the distance from here to here, this is x minus 1 minus mu star. Okay. So, this becomes x minus 1 minus mu star whole square. Okay. And another one due to this will be 1 minus mu star, which is the mass of this particle. Okay. So, the distance is total from here to here is this this distance we have taken from here, this is the distance taken from this place from the barycenter, this is the distance x. So, the distance from here to here will be x plus this distance is mu star. Okay. So, this becomes mu star, and omega square obviously on the normalized scale omega square equal to 1. Okay. We have already worked out all these things. So, once omega square is equal to 1 this quantity. So, simply what we get x is equal to mu star 1 minus mu star divided by x plus mu star whole square and plus mu star divided by x minus 1 minus mu star whole square. Now, compare it with equation number f that just now we have written. Okay, look into this equation and the equation number f that we have written here in this place. Is it the same? This x is equal to 1 minus mu star divided by x plus mu star square and then mu star by x minus 1 minus mu star x. So, here through this route it is a very easy to write. Okay. Similarly, for the point number, this is for the smallest mass. Okay, these are the two primary masses and this is the tertiary mass, which is infinitesimally small as compared to these two. So, as not to disturb the motion of these two. So, under this assumption we are working. So, if the point is lying here, the same thing can be written as omega square x is equal to x equal to, now we look into this mass is pulling it in this direction and this mass is also pulling in this direction, while and these two together provide the necessary centripetal acceleration. So, if we balance all these forces, so what we get here 1 minus mu star divided by, and the distance now from here to here, this distance will be. So, this distance if we write from here to here as x. So, this distance becomes x minus mu star, okay, because the distance we are measuring from the barycenter. So, if we subtract this mu star from this x, so what we get is x minus mu star. So, this whole square, and similarly for the second mass which is m 2, this we write as mu star divided by, and here the distance will add x plus 1 minus mu star whole square. Now, you compare this with the equation number E. Okay, so equation number D. So, now look into this equation, isn't it exactly it is the both are same. Okay. So, in a very simple way using this figure we have been able to work out this problem. So, instead of doing so much manipulation, if we work the normalized scale, so it is a very easy to look into what is exactly it is happening. Okay. Okay. So, lastly we are left with the point number 1. So, now work for L 1. So, we have the mass here m 1, here this is the mass m 2. Now, the point is lying here in this place. Okay. So, to work out for this again b is the distance here, this is L 1, okay. This is the distance x, and this is the distance from here to here, this is the distance 1 minus mu star. So, this distance will be one minus mu star minus x, and the distance from here to here, this will be this 1 minus mu star. We are considering the point this one. So, distance from L 1 we are taking from L 1, not from here. So, this distance becomes x plus mu star. So, this distance become x plus mu star. So, considering the mass m 3 here in this place, now you can see that this mass is pulling it in this direction, while this mass is pulling it in this direction. So, this is a different case than the previous two, because here the two gravitational forces are opposing each other. Okay. And then since the barycenter is here, so this mass will also move along with this about this barycenter. So, the whole thing is moving with the same angular velocity. So, it will go like this suppose. So, if it goes like this, then the angular velocity being the same as the angular velocity of m 1 and m 2. So, to provide the necessary centripetal acceleration in this place. So, what we need to do, we subtract the from the this gravitational acceleration, we subtract this gravitational acceleration, and that will provide the necessary centripetal acceleration to move in the orbit around this barycenter B. Okay. Okay, so, we have from here omega square x is equal to x, because omega now in this case equal to 1, and therefore, this quantity then becomes mu star. This is the mass which we have written as 1 minus mu star, and this is the mass we have written as mu star. Okay. So, 1 minus mu star So, divided by the distance between this and this point, the square of the distance. So, this distance is x plus mu star whole square, and then from this what is to be subtracted? The force due to the mass m 2. So, if we subtract the force due to the mass m 2, so that becomes mu star divided by 1 minus mu star minus x. This is whole square. Okay, so, this implies x is equal to 1 minus mu star by x plus mu star whole square minus mu star divided by x. We can take out the minus sign and the square, obviously this will not matter. So, this matter. So, this becomes 1 minus mu star whole square. So, this is our equation number D E F. We write this as the equation number G. So, this can be further written as x times x plus mu star square times x minus 1 minus mu star whole square. This is equal to 1 minus mu star times So, this is another quintic. Okay, so, let us write this as equation number G 1. Equation number G 1, and this as our we have written as the equation number if we can note as this, and this becomes equation number F 1. And another equation that we got this was equation, this we have written as Z. So, rather we can write this as E 1. Okay. So, 18, 16. So, we have E 1 from E 1 equations E 1, F 1 and G 1. These three constitute 3 quintics, and solution to this three equations will give the 3 vibrational points L 1, L 2 and L 3. Now, remember the way we have shown here, the L 1 lying on this side and L 2 lying on this side, and L 3 lying on this side, L 2 lying on this side, and L 1 here. This is quite arbitrary. Many of the books may refer as the L 1 as this, L 2 as this, and L 3 as this. Somebody may refer this as the L 3 point. So, do not get confused with this. Okay. So, this convention is totally arbitrary. So, in the next lecture we continue with this. So, we will directly write the solution of we will little bit simplify this E 1, F 1 and the G 1 equation. So, you will see that it will appear in the form of these equations will appear in this format A 0 plus A 1 x plus A 2 x square plus A 3 x cube plus A 4 x 5 A 4 plus x 5 equal to 0. So, this will basically constitute a fifth order fifth degree polynomial. This is a fifth degree polynomial, okay. And these coefficients next time we will write for all the three equations E 1, F 1 and Z 1. So, thereafter we will proceed to work out with the Jacobi's integral that we have got, okay. And in that Jacobi integral they will see how the things are taking place. So, the next time what we are going to do the Jacobi integral, which will the Jacobi integral solution, it will look something like this, what is shown in this figure. Okay. So, from there next time we are going to show that this the shaded region is non accessible region, and the non shaded region that is the only accessible region. So, how this is taking place? So, we will conclude this restricted 3 body problem in the next lecture. Thank you very much.